All right.
Okay. Welcome to, I think officially today is almost the last day for the course, although we always go on.
We got next week's speaker.
Okay, so next week you get great. So this is the second to last. And I'm really glad to see so many people here because this is a topic that initially, I don't know how we start talking about the causal inference. And I always wanted you or somebody, I always wanted to say, well, does astronomers care about causal inference? Because we work so many years that never come up in any way. But my department, there are many people do causal inference, right? In social science, in epidemiology, medical science, you always talk about, what thing you can change to really make a difference. And so then, we have Souhardya has been studying, working on the causal inference. And so it will be great to have kind of introduction to really understand what it will be interest to the astronomers, but apparently there are interests, right? There are some articles already showed up. So I think this will be kind of new for the CHASC group to explore. Although I know CHASC group is very ambitious. You're thinking about now explore quantum computing last night. So we're getting to all the field that we usually did not really touch. So I'm really glad to have Souhardya here. Souhardya is he's a graduate student here in the department. I don't remember which year, but that's okay. Second year? Okay. So you still have like another 8 years here? No. Okay, but so he's going to give us like a quick tutorial and then talk a little bit about the relevance for the astrophysics. Oh, you are here. Oh my God. Good to get you here. Good to see you here. Okay, so then you should take the food. And...
this is
no. Basically, pick one.
This is Jiaoli.
No, it all has my name on it because it's my. Don't be confused by it.
Yeah. There is no causal connection.
You don't need the plate because essentially you take the whole thing. So whatever you like.
Yeah, American size.
It's true.
Oh, you take the whole thing.
You take the whole thing. That's my name. Just don't take these two with somebody's name on it, right? That's yours.
Oh, so that's the
Jima, this Alan, this for somebody else.
Okay, I'm good.
But there's all these. I don't know what these are.
Oh, wait, sorry. I took the same thing.
Okay. There's somebody else.
Yeah.
Okay. Yeah, you're the. Okay. So I can take.
I can have
People here.
Oh, you can have the chicken curry.
Oh,
Yeah. Okay.
All right.
All right.
Continue then.
Sorry for the interruption, but keep going.
All right. Hello, everyone. Thank you very much for coming here. So I am Souhardya. I'm a second-year PhD student at the Department of Statistics. And this talk intended to do a lot of things, but probably this talk is primarily going to focus on the first part. So we are going to get into a tutorial on causal inference. I might go and talk about some methods that, we are interested in astrophysics, but I probably won't be talking about astrophysics per se, so not use like astrophysics terms. So I primarily intended this to be a tutorial on causal inference. We'll start from the very basic. Not really plan to go into much technicalities, but let's say give an like overview of how really we even think about it. All right, let's start. So, oops. All right, so I'll start with a hypothetical motivation is this example. So it says that there's a group of researchers who claim that they have this treatment when you do it to a child during their ages of 1 to 2 years old, then the child has much lesser chance of developing diabetes when they grow up. And they even present you data that they show that, so they give you some kind of an experimental evidence that they did this thing, they did a survey on adults, and they show that among the stratum of people who actually went through that treatment when they were young, they have much, among them, the incidence of diabetes is very low. So yeah, it's a hypothetical example. So suppose you are presented with this information and you're presented with the experimental evidence, would you recommend this treatment to others? Now, okay, this do sound like a trick question, so probably you are more tempted to say a no. But suppose I'm a layman and I don't reason that much, And then I see data, and my data shows that, well, most of the people who went through this treatment, did not, have much lower chances of developing diabetes. So I might be very confident because, if you get the treatment, you're having lower diabetes. If you don't get the treatment, you have higher instance of diabetes. So as a layman, I might just by looking at this information say that, well, I want to recommend this treatment. But suppose now you learned something, a plot twist. You find that most of the people who actually got this treatment in 1 to 2 years of age, they die before the age of 40. This one line completely changes what you actually were thinking about the treatment. It's not that the treatment was causing the diabetes to go down. It's just that the treatment was killing you before even you could reach an age where you were more probable of getting diabetes. So just this one line completely changes of what you thought about this treatment in the first paragraph. So why did this happen? What exactly mistake I did as a layman? I reasoned like this, that, well, you get the treatment and you have lower chances of getting diabetes. What I was doing in this entire exercise was that I was seeing that, doing this treatment is correlated with having lower chances of diabetes. And I mistakenly also took it by saying that probably this also means that, doing that treatment causes me to eventually get lower chances of diabetes. But that is not true. I confused between the two terms, correlation and causation. I thought that just being correlated with lower chances means that this caused lower chances. And in general, they are two different. So this talk is actually going to see, like, what exactly do you mean by causality? How do you even establish that something is causing some other thing? And how statisticians approach this problem, and what kind of things do they do? All right, so let's not talk about statistics for a while. Logically, how do you even establish that the treatment caused an effect? Because the problem is, if we look at whatever we are observing, it seems that we can only establish correlation, right? The most thing that you can do is that you look at whether you were treated and you calculate, like, among those treated people, how many of them develop diabetes? Among those untreated people, how many of them develop diabetes? So it seems that if you just look at the things that we've observed, we can just establish correlation or association. How do we establish, like, causation? And this is basically the key idea, that you ask the counterfactual question. So you ask this question, like, what would have happened had the treatment not been administered? For example, if you give me a treatment and my probability of developing a disease goes down, there can be many factors that actually causing the disease, that probability to go down. It might be that I am inherently, I was inherently even supposed to have lower chances of disease eventually. So you ask this counterfactual question, like, what would have happened had you not administered the treatment? If the answer to this question is that, if I did not got the treatment, I would have higher chances of developing a disease, that means the treatment makes a difference. Otherwise, it does not. But usually the question is like, how can I even know this answer to this question? Because, once you give me a treatment, you don't know what happens to me if you would not have given me the treatment. So statistically speaking, what I was saying in this first point is that, you can go and whatever quantities maybe we are familiar with this far establishes correlation. So for example, suppose you have n subjects and you're collecting a response yi from each subject, and you're also collecting their treatment status. By treatment status, I mean like a binary number.
Good question. So about this key idea, how is that not dealt with by control groups?
Yeah, precisely that. So that's precisely how we do it. And that's exactly what I want this to be a motivation for it. But yeah, there are some subtleties, which I'll probably dive into. Okay. Yeah, so this is like very layman introduction, like knows nothing about scientific experiments. Okay. Precisely the idea is that we will create control groups, but okay. So what I was saying that, yes, we talk about, we know this term correlation, which basically kind of is a measurement of association between treatment and response. And by the way, by treatment status TI, I would mean a binary variable. So 1 would imply that that person is treated, 0 would imply that that person is not treated. So we know how to calculate correlation, and we just established that correlation does not imply causation. What this means is that we need different quantities that establish causation. So we are going to talk about some statistical quantities that says that, well, if this is positive, means that there is a causal effect. All right, so this is kind of a motivation on why we should even think about causal inference and why is it relevant in science. Now I will start with the statistics. Okay, so this is the potential outcomes framework, which is one of the most popular framework in which we establish causation. This was developed by Donald Rubin, who was in our department, and I did not have a chance to meet him because he probably left before I came here. But so this is a very simple framework. So so this is how it goes. So suppose you have n subjects, and you have some treatment, and you either administer a person a treatment or you don't, and that is, let's say, reflected by this treatment status Ti. So if Ti is 1, that means that person was treated. So what the potential outcomes framework does, it assumes that, hypothetically, I assume that there are two potential outcomes which I do not observe corresponding to each individual. So there is an outcome yi0 that individual would produce if he was not treated. There is an outcome yi1 that individual would produce if they were treated. Now, what actually the administration of the treatment does is that it reveals one of these outcomes to me and hides the other one. So for example, if you treat me, I know yi1, but you have no way of knowing what yi0 was. So, and also we usually assume consistency, which means that, I reveal exactly the same outcome whose treatment you assign to me, but sometimes this is also under question. So that's why I'm actually calling it an assumption. So this assumption of consistency means that, I am revealing exactly the same potential outcome that, you are administering corresponding to the same treatment. So I'll assume that. So this is precisely we will assume that this is precise. So the framework assumes that this is exactly how the responses are getting generated, is that you are giving me a treatment, and I am actually observing the response corresponding to the treatment that you have given me. Okay.
Can I actually, because I want to have a little discussion how to relate to the astronomy problems. So I want to ask about, well, you got interested in astronomy. Is there some kind of thing you actually want to know this counterfactual? Is there some counterfactual thinking there in your problem? Say, had the star did not grow, whatever actually happened? Is there something of that nature? Because in the medical treatment, it's very clear, right? You want a treatment fact is what could happen if I want, I don't want to see anything else, but that's a counterfactual way of defining treatment effect. It has its own limitations. One thing is already hidden here, the consistency. The consistency is not a trivial assumption. Consistency means a lot of things, like it's not like what treatment you get, for example, is like who's giving you the treatment. It could have changed things. And who else is getting the treatment at the time you're getting the treatment. There's all kind of hidden stuff there. You want to make sure. But I want to think about to really drive the causal question. Is there something from your perspective say, hey, that's the way we think about it? We say, well, that's not relevant.
Can I take a stab at that?
Sure, go ahead.
So for one, let me start with a slightly different question. People often complain that astronomy is not science because you can't do the controlled experiment. But my answer to that is usually if you have a billion of something and you're allowed to sub-select your samples that you're looking at to ever finer details and say, conditional on this, the probability of this is this, then you're effectively back to doing controlled experiments. You just need a vast number of examples, and then you can kind of do a controlled experiment again. So I do think astronomy is actually a science. So then something that goes along with that, then, though addressing your question, is we're not doing this kind of thing because we want to influence the future. The medical professionals want the patient to get better. What we're trying to do, though, is accumulate evidence for or against the hypothesis. And so if we've got some hypothesis, the stars that form with more dysprosium in their stellar atmosphere do the following. We might have a hypothesis, and so we want to kind of do the analog of the controlled experiment that tests that hypothesis. So we can still ask counterfactual questions and try to get at them by using large samples of data. So I think there's a very good analogy to this.
So that's a really great one because actually, I'm teaching another course and which is like yesterday, Tuesday, right? We talk about the relationship between causal inference and multi-resolution inference. Multi-resolution is just saying you have different, you ask deeper questions, right? And this is exactly, I think, another way of saying about is conditioning. Because these causal questions is all depends on at which level you ask that question, right? Because when you treat the individuals, and the individual is not an individual. The individual has a time component to it, right? Yeah. Are we treating a period? Are we treating, there's all these very detailed questions, right? And I was also thinking about there's a little bit of maybe too much that, what is exactly the causality from a kind of philosophical point? Is like something that exists that if I go all the way, regardless of the resolution, is that relationship always exists. It seems like much stronger than at some level it existed, right? So I guess your point is that if you have enough data, then essentially you can take like a nature has run experiment for you. You just need to find out what are the conditions informs what the outcome is.
Yeah, and is a billion enough or do you need a trillion? But it seems like in some limits,
yeah,
multi-resolution inference and causal inference become the same thing.
Yeah,
right. I'm saying words that sound good to me here.
Yeah,
it's tell me about
just to give a concrete.
Yeah.
Jeff has his hand up, but Jeff,
Great.
just a minute. Just want to take off from the point that Doug made that there is a concrete example. For example, is that suppose you have planets close by around M star, and you want to know how much of the atmosphere is still left. And people have been doing this measurement and finding that almost all stars in the so-called habitable zone are rocky. They're pretty much their atmosphere has been blasted off, presumably by flares on the star. But there are some which do have atmospheres. So what is the connection? Is it because that star did not have as many flares? Is it because the planet was had a magnetic field? There are issues where one thing can happen versus another thing can happen that we would like to find out what caused which,
okay, so
which we don't have an
okay.
exact theory of yet.
Say galaxies and supermassive black holes and bigger galaxy forming the dense environments. What causes the galaxy to go? There are questions, a lot of questions which relate to evolution of structures.
And I'm thinking about because the reason the causal question becomes so important in medical epidemiology, all those things, because they don't have so-called a hard theory, right? It's these causes discovered by empirical results. That's what the causal inference is about. And I guess probably people's perception is like in physics or astrophysics, you have the grand series to kind of tell you what it is. But I guess that's probably true to a certain extent, but anything based on empirical observation, you're deriving a theory and you still have similar kind of question. Trying to, is that right?
Jeff had his hand up.
Jeff, go ahead.
Yeah, I'd like to push back a little bit on the comment earlier. I'm not sure who made it, that because in astronomy you can sub-select data, I don't think that really gives you any handle on causality at all. It gives you a handle on correlation. Maybe I'm missing the point, but you still don't know if there's something else causing both things and so on. The usual problems with causality. So, of course, I defend astronomy as being a science, but it's an observational science, and I don't think there's any real way to get a handle on causality just from the data. But maybe the rest of the talk will show how that can happen. I don't know if I'm making sense, but just sub-selecting data that has a given property, you still don't know any more about causality, in my opinion.
We should let the speaker continue, but just very briefly, I think it depends when and how you do the selection, yes. Right? So I guess I'm referring to a limit where you essentially have an infinite amount of data for all practical purposes, so that as you develop hypotheses and want to test them, you can continue to select things that you haven't seen before effectively, right? And then it becomes more like an experimental science. But yeah, I mean, I agree with you, Jeff, fundamentally. This is Doug Finkbeiner, by the way, from Physics and Astronomy. I agree with you fundamentally that it's still just correlations and not causation. It's just that as the amount of data goes to infinity, it becomes more like an experimental science.
You have, go ahead, yeah.
I do have a question. So far you were talking about correlation and how correlation is not causality. Did you define what causality is? Was that something you were going to do?
Yes.
Okay.
Yeah, not yet. Yeah.
I just interrupted him, you know.
That's all right.
Okay.
Go on.
Okay, no, but I do think that these are like serious questions. Like if we cannot do a randomized controlled trial, sorry, I'll define what that is. If I cannot, do an experiment just from observational data, can we even establish causality? I do plan to, let's say, touch on those kind of aspects. Hopefully I'll be able to. Okay, so I have talked about the potential outcomes framework, and based on that, I can actually now define something that is called an average treatment effect. So the average treatment effect is defined as the expected difference between the two potential outcomes. And note that this is an expectation over a counterfactual quantities, because you really cannot observe both of them simultaneously. So this is called an average treatment effect, and this is actually what we call a causal estimate, in the sense that if my tau is positive, that means that if you give me the treatment, I will on an average show you a higher outcome as compared to if you did not give me a treatment. So for example, if tau is, let's say, so for example, saying that my treatment has a causal effect is the same as trying to test whether tau is greater, whether tau is equal to 0 with the alternative whether tau is greater than 0 or not equal to 0, whatever be the case. Note that, so this is a population quantity. So I am interested in the average treatment effect of a population. In reality, you will never be able to evaluate this quantity for a particular individual because, again, you do not observe both of them. So these are called individual treatment effects. Like yi1 minus yi0, they are called individual treatment effects, but I'm interested in estimating an expected value of it. Although there are some recent developments that kind of allows us to do some kind of inference on this individual treatment effects, but I'll go into that later. So this is an example of a causal quantity, which is different from correlation.
What is the expectation of where's the randomness?
Okay, so there are, so I decided to be a little vague on it, but there can be multiple things. So usually I can assume yi1 and yi0 to be both random variables. So assume that both your potential outcomes are random along with my treatment assignment tree. So this is an expectation over the population yi1 and yi0 have been drawn from.
Okay. You could just think about, you don't even need to invoke a randomness at all. Just think about you have a population, right? Everybody has a potential outcome, right? Then you say, well, I care about a potential outcome for this population. Then you just average your eyes, just like what you said by doing the group, right? And then the real problem is, in most times, as individuals, we're not interested in that quantity. We're interested in the individual for me. But this is the kind of a way to get around because we don't know how to estimate the individual ones, at least we can get these average ones. Now, the relevance for this one is because, anytime you take medications, right? The FDA approves all these medications through clinical trial. Clinical trial is really never about how the drug works on you. It's about how the drug works on our population. And we take a leap of faith. We take a leap of faith, say, well, if it works on the population, it kind of works on me. The doctor takes that leap of faith, but the doctor is fine. But doctor's fine, so they're treating lots of patients, there's an average effect. For individual, that's not fine. So part of the stuff I do is on this individualized treatments, much out of question, right? And that's where I started doing the multi-resolution one. Just think about the resolution goes to infinity. That's where you get the individual. So this is what the statistician way I've been doing it. Say we estimate all the treatment effect, but this framework now is being pushed to the boundary because of all these newer technology. For example, the individual you wear a device, how much exercise you're doing, your blood pressure. Now they want to kind of say, if I implement a regime for you, say you run for 20 minutes, you don't do like how that affects you. Now you're talking about one individual, right? Now you can push on the boundary, and then there's always a leap of faith from the population to the individual. But mathematically, it's most clean to define this average because the fundamental question about how do you define even probability for a single individual is not an easy question. So that's where the connection comes.
Okay. Yeah. So, okay, probably I won't, but if I get to the very end of the talk, so there are some recent advancements using conformal inference, which actually allows you to find confidence intervals for individual treatment effects without any assumptions on your population. I might want to talk about that a little bit, but let's.
Well, they still make assumption that you're exchangeable with others.
I mean, of course.
The information can accumulate from others.
You're really gonna have to do something. Okay. Anyway, so this is our causal estimate of interest, and now we are going to talk about how to do inference on it, like how to estimate it, how to test, whatever. So here is how do I do this? So there is a very an experiment which you can do. It's a very simple experiment which you can do to estimate the average treatment effect. This is something we call the randomized control trial. And okay, let's describe that first. Okay. So you are a researcher, you are in control, you have a treatment, and you want to estimate the average treatment effect for your treatment. So what you would do is you would do this. So you have, let's say, n subjects. What you will do is that for each subject, you will take a coin and independently you will toss the coin. If it turns heads up, you will treat that subject. If it does not turn head up, you will not treat it. So this basically divides. So what you have done is you have divided your subject randomly to a treatment group and a control group. And the division you have done is completely exogenous. Like you have not looked at the subject while doing this division. In that case, basically, for the treatment group, you observe their treated potential outcome. For the control group, you observe their your untreated or controlled potential outcome. Then there is a very simple thing you can do. So if you remember, tau was a difference of these two expectations without the hat. So what you can do is you can get a simple estimate of this expectation. So expected value of yi1 is basically the average outcome for the treated group because they are all producing the treatment potential outcome. Expected control outcome, estimate of expectation of yi0 is the average of the output from the control group because they are all producing a control treatment outcome. And then you have a very simple estimate of tau, which is your ATE, which is basically you take the two difference between these two things. And this is a very reliable estimate of tau hat. And this kind of solves a problem. But we are not done yet. Because as we will now argue that, this privilege of even trying to do a randomized control trial, that is very rare. In most of the settings, you do not have the privilege to go there and, and design an experiment. For example, suppose you are trying to assess whether smoking causes lung cancer or not. You cannot do an RCT and ask a group of people to start smoking and see whether they're developing lung cancer when they're old, right? So for many ethical reasons and many other things, you do not have this privilege of doing an RCT. So what actually happens if you cannot do that? Okay. All right. So such studies where you do not have this privilege, where this experiment has been done before, and you're just merely observing the data are called observational studies because you're observing the data, and as a scientist, you are not have this privilege of going out there and doing an experiment. So, okay, why is this such a big deal? Why is observational studies, such a big deal? Why am I even trying to distinguish between these two studies? So let's take observational studies. So what that means that now I have just observed data. I have just observed yi and I have just observed ti, and that's just it. And let's still take the task of estimating tau, the average treatment effect. Right. So let's ask a simpler question. So if you remember in the last slide, I estimated this expectation of yi1 by the average of the treated potential outcome that the treated group produced. So the question is, can I do that same thing here as well? Is that an unbiased estimate? The answer is no, because this actually is not an estimate of expectation of yi1. but it is actually an estimate of expectation of yi1 condition on ti equal to 1. So it is an estimate of the treated potential outcome of the treated group. Now, and this in general might not be same as expectation of, let's say, the treated potential outcome of the overall group. As an example, suppose you're doing this hypothetical experiment where you want to know that if a person has higher, if a person has higher education level, are they, let's say, more likely to have, be healthy during their later stages of life? Now, the problem is if you just look at the people who, basically if you just look at the people who actually attained good education, and if you just look at their, how healthy they are eventually, that has kind of a confounder. So it's not that, attaining education makes you healthy. So there can be a confounder. For example, rich people are more likely to complete education, and rich people are more likely to be healthier because they are, they can afford better healthcare. So in general, basically, if you just look at the treated people, which in this case means the people who have attained education, you might be actually restricting yourself to the group of people who are rich. So this potential outcome for the rich people is not a representative of the overall expectation. Then why was it not a problem for the randomized control trial? Like what exactly happened? I use exactly the same estimator for an RCT. Why was that not a problem? It is because of that precise randomization step that I did. When I allocated the treatment, I was not looking at the subjects. This randomization broke all that association that the treatment assignment had with the potential outcome. So for the randomized control trial, conditioning on ti equal to 1 was ti and yi was independent. So basically this unconditional expectation was actually equal to the unconditional expectation that we wanted to estimate. And that's precisely why RCTs are such a privilege, because if you can do an RCT, you don't need to worry about anything, because you have, and this is basically the fundamental problem of causal inference, that your treatment assignment might be linked with your potential outcomes. If you can break that tie, you're good. But in an observational study, because you don't know how the treatment assignment was done, you really don't have a way to break that tie.
So this, when you make this assumption, when you make this equivalence of the conditional being equal to the sample, you're also making an additional assumption that the treatment is Gaussian, or it has a small coverage, because if you have power loss, which we find all the time in astronomy, I don't think you can ever write that.
I don't. So this is just whatever this assumes is just written here. So for a randomized control trial, what I'm saying is that the treatment allocation is independent of my potential outcomes, right? I'm not trying to test anything here.
Right, no. What I'm saying is that there may be situations where you can never have this randomized control.
Exactly. That's precisely why observational studies are so hard. That's precisely why we are even talking about observational studies, because I do not have this privilege. I cannot assign treatments, right?
I guess I think these are two different points.
Okay.
Vinay is talking about if you have a specific kind of distribution, may not happen.
Yeah.
That's actually not true. This always happens. This can always happen.
Even for power law?
It doesn't matter which distribution, because this is you might be thinking about if the power law, maybe it's not good. Average may not be representing the curve well. That's a different question. This is always defined. The estimate here. It's very interesting. This is always defined the estimate at the average.
Okay.
Now there is a subtlety here, because you say, well, why do we define the causal effect is the average differences, right? Now, typically because these binary outcomes are 0 1s, you get to treat it better or not treat better, so it's like probability compare. Even for that, you say, well, why don't you compare the ratios? Like one has 5 times more accurate than the other, but you will see the problem this breaks down. This average, the average allows you to, the average of the difference is the difference of average because of the linearity of the average. So you can, when you talk about the average of each individual, you can estimate according to the marginal distribution without worrying about their correlations. That's the magic of how do you estimating, because you never observe, for example, we never know how the two potential outcomes will relate to each other, right? You can only observe one. The average allows you to switch the hand. Like you can get one group of people, a separate group of people, you take these are different averages, but their average itself is all unbiased estimator for the population mean. So that's relying on that ability. If you do ratios, we don't know what's the average of ratios. It's not ratio of average, right? So, but this is purely just saying that you would allow, if you have Y's independent of something, then its conditional expectation is just like unconditional. That's all this says.
One more question. When you talk about randomized control treatment, I see. So at the beginning, you need to have a big population from which you start selecting this randomized samples, right? Because if you are in one big city and you do the study in one big city, it could be completely different than the other one where the conditions of people would be different. So in astronomy, when Doug was talking about selecting from the video of objects, that's probably where you would go into this randomized control experiments.
Yeah. Although, if I could say what Jeff Scartle's probably thinking, that doesn't really get you away from the problem because there can always be other confounding factors that you have not thought of.
It's also here.
So unless you're directly making an intervention on those randomly chosen samples. But then my answer to that would be, sorry, Jeff, I'm having a debate with you. Is like how you proceed there is to predict something that you otherwise wouldn't have predicted.
Right.
Like you say, oh, okay, we think we've learned something about stars. Now that predicts there will be 1,500 vibrational oscillations of the sun with these patterns. Then we build a big telescope and go measure them and find that those patterns are there. That's called astroseismology. And things that you would not have predicted unless you understood the system. So then you go out, you gather data, you say, oh, look, we were right.
I actually wrote that in the comments, and Jeff responded to exactly that by saying, good point. But theory does introduce an important element. What we're saying here is that you're leaving the arena of data is the only thing that you believe, because there is a theory connection that we're relying on to make this translation.
Yeah. No,
I was being a little flippant there. That sure, adding other confirming relationships adds to one's belief in the causal relationship, but it's sort of an indirect thing. Anyway, sorry to interrupt, but this is all very interesting points.
No, I totally agree. So I'll amend my original statement to say that an infinite amount of data is not actually enough. You still need some theoretical component that modifies what you look at next.
Well, I guess the big point here is that don't think a statistician figure out a way to do actual causal inference. Nobody can. Right? I'm serious. Nobody can. Okay. I mean, unless because you can never rule out there's some bizarre confounding factor you just didn't know. Right? Even the truly randomized experiment in real life, if anybody run a clinical trial, they will tell you that that's just when we make effort, because when you randomized, you give that patient a treatment, the patient still decide whether they want to take or not, whether to take all the medication or not. If I have a more serious disease, I would take all kinds of other stuff without any of your control. There's always a compliance issue. There's always issues there, right? Even if it's a purely randomized, you only randomize once. It's a still statistical argument. What we try to do here is to say, just like do any statistic, we never claim anything 100%. That's the beauty of statistics, right? It's just that we're trying to make them more likely, give you more confidence, right? Doing this, more likely you're going to eliminate these, really bad confounding factors. But in the end, at the end of the day, there's always a guessing component, right? We're just trying to make the kind of guessing component it's an educated guess as correctly as possible. Rule out all these, things, and so make the things as scientific as possible, right? Statistics is always a part of, luck, art, engineering. It's not entirely scientific. I can say statistics is not entirely scientific. It's fine. Like you cannot say astronomy is not science. I can, right? Go ahead.
Yeah. Sure. Okay. Cool. Okay. All right. So So what we established in this slide is that this estimator, which also kind of seems very natural to very natural that, for example, if I want to estimate this, I'll just take an average of the outcome of the potential outcome of the treatment group. This simple estimator that might feel intuitive to someone is actually not the right estimator because it is not estimating the right thing. So what do we do in these situations? Like, what is the right estimator? So, okay, so the question is, what exactly went wrong? This is something I went over already. So by tau 1 hat, I mean that that estimator, that was the average of the outcomes of the treated group. So that is a good estimator for your expectation of yi1 only under this assumption that your treatment is completely independent of your potential outcomes. And this is generally not the case for observational studies. So what is the estimator here? So the idea is that, again, we need to make an assumption. So we need to make an assumption which kind of tries to understand this association between TI and the potential outcomes. So what statisticians assume, and this is more or less a reliable assumption in many scientific experiments, is that any association between yi1 and yi0 and the treatment, the potential outcome in the treatment, any association that's coming there is because of a set of covariates, xi's, which can be like multiple information that you pick from each unix, which we call confounders. Okay, so for example, here is exactly the same example I was giving, that rich people have access to better healthcare facilities and have better chances of surviving a disease, and they also, rich people are also more likely to be able to afford better education. So in this randomized controlled trial, so in this observational study between where I'm trying to assess the how your educational level affects your healthcare, whether you are rich or not is a confounder. And the assumption that I'm going to make here might feel dicey, which is that I'm going to assume that I observe all possible confounders that exists, right? So this is usually called the unconfoundedness assumption, is that it says that all the xi's which actually can quantify association between this and this can be observed, right? And later on, I will basically talk about what happens if we do not observe all the confounders, because that's really the more relevant setting. And turns out there's not much we can do about it. So statistically, I write this unconfoundedness assumption as this conditional independence. I say that once you have observed my covariates, now whether I'm getting treated or not is completely independent of my potential outcomes. So any association between these two guys, the potential outcome and the treatment, is solely coming through the covariate. Once I know the covariate, they are independent. That's something we call an unconfoundedness assumption. So I would like to highlight that in this assumption, the questionable part is that we are assuming that I observe all the xi's. So yeah, that is the questionable part. Assuming this independence is actually not a bad thing. So this independence assumption is actually exactly translating to what we were actually thinking here, that xi's capture all possible association between the potential outcome. So what I'll do is I will assume this unconfoundedness. This is like a classical thing that we assume in causal inference. And I will show you okay, then how we can actually get an estimate of the average treatment effect here. Right, so, okay. So let's talk about this same problem of estimating expectation of yi1. Similarly, we will be able to estimate expectation of yi0, and we'll take the difference. That will be our estimator. So, for the sake of simplicity, we'll just consider estimating expectation of yi1. So we have an assumption, right? That which is that given xi, the potential outcome and treatment are independent. So under this unconfoundedness assumption, we can define the propensity score. Well, we can always define the propensity score, but it makes sense if we are under this assumption. So we define the propensity score as the probability that you are treated given you have a particular covariate. So for example, it can be something like, if you make this much amount of money per year, what is the probability that you actually, you attain a particular degree? For randomized control trials, this quantity is in the hand of the statistician, because this is precisely the probability that the coin toss that I was doing will land heads up or tails up, right? So because for randomized control trials, the statistician is not looking at the xi. So therefore the treatment is independent of xi. So what happens there is that pi x is always going to be constant for the treatment group. And what that probability is also under the control of the statistician. And usually it is half. So for example, with probability half, we will assign people to treatment or control. But in general, pi x is, in general, pi x is not half. And it actually depends on my observational study and how my treatment was collected. That's how I get my pi x. So the thing is that this pi x is a probability. It's a theoretical quantity. So in principle, you can never actually observe it. So you cannot look at an observational study and exactly tell me what was the probability, because you can only estimate it, but you cannot see it directly because it's a population quantity. But okay, so the way we are actually going about it is like we are making all sorts of assumptions that we can make to even arrive at an estimator. And then we will see like, okay, what happens if this assumption does not hold, this assumption does not hold, right? So let's assume that we know the true pi x, right? If we know the true pi x, and I'll also assume something called positivity, which means that pi x is strictly between 0 and 1. What this means is that every unit has so every unit is not surely a control unit or not surely a treatment unit. This assumption is actually going to help me derive what estimator I'm going to derive, but this it might look like a harmless assumption, but there are many settings where this assumption does not hold true. For example, we have for example in like incentive programs where government, let's say, pay someone cash rewards if their, let's say, some earning is less than a particular threshold. In that case, this positivity assumption does not hold true because anybody whose income is below a threshold, they are always in the treatment group because they are always getting the incentive. And anybody whose income is above the threshold, they are always in the control group because they will never get the incentive. So in that case, pi x is either 0 or 1, exactly. So this does not hold always, and therefore the methods I'm going to talk about will not hold in those settings. But usually this is the case that this assumption encompasses a large variety of scientific experiments we do. So, okay, so we talk about something which is called an inverse probability weighted estimator or an IPW estimator, which actually is basically taking the sum of the treated outcome. But now it is not actually taking a usual sum, but it is taking a weighted sum. And the weights are the inverse probabilities, by which I mean like 1 over pi x size. So what I'm doing is instead of taking the vanilla sum that I was doing earlier, there's a little difference in the factor that was appearing here earlier. But in general, instead of the vanilla sum that I was doing, I'm now taking a weighted sum, and then I'm dividing by 1 over n to take the mean. And I claim this to be an unbiased estimator of expectation of ii1, right? So to just build some intuition, what this thing is actually trying to do is it's trying to reweight my my treatment group, which is the people who were treated, and trying to make it look like the overall population. Why so? Because so for example, suppose that pi xi is very high. So assume that pi xi is very low. That is a better motivator. So pi xi is very low, implies that that particular unit in the treatment group, they are much less likely to actually belong to that treatment group. So what I'm doing is I'm basically increasing the weight for that unit. So 1 over pi xi would be large if pi xi is small. I'm actually increasing the weight of the unit so that my IPW estimator put more weight to a person who was less likely to be in the treatment group, so that I am not, let's say, biasing myself towards the treatment. Similarly, if pi xi is large, then 1 over pi xi would be small. So if a person is more likely to be in the treatment group, I'm actually giving them less weight because, again, I want to not restrict myself to the treatment group. So whoever is more likely to be on the treatment group, I'm downweighting them. Whoever is less likely to be on the treatment group, I'm upweighting them. And you can do some, yeah.
So it seems like that is not normalized, right?
This is not normalized.
The 1 over n front should be 1 over the total number in the group or something. Or that you need
No.
to divide the whole thing by the sum of inverse pies or something, I mean.
Yeah, so,
Something doesn't
okay,
seem right about that.
right, so basically, but it turns out that this thing, right, there's just these expectation, that turns out to be an unbiased estimator of, the sums. So
Okay.
this turns out to be an unbiased estimator of sum over yi1, where I runs from 1 to 1.
Okay.
And then you divide by an n so that you actually get an estimator for that. So it's a little, so the motivation is a little different.
Well, there's an important point here, because this is a kind of a, you're right. There are two estimated here. One is you can self-weight this. You can weight divide by whatever pi, but that sum, it will converge to, on average, it converge to 1. Just because the way it's, if you look at the pi axis, if you average over all the axes, that's just how many people gets treated. So that's, and the n here will be automatically, I think that the way you're writing it, you should have the original one, you should have the denominator there. There's a sum of TIs. Right, because even the original estimator, that's average over all the treated per person. Yeah. So it's not a 1 over n, it's 1 over sum of the.
Yeah.
Actually, so maybe I've just misunderstood. That n there is the total number.
Yeah,
of
it is
people?
not the number of
It's
treated
not the
people, it's the
number.
total number.
Okay, oh, and then TI is 0 for the untreated people, so that doesn't contribute to the
Okay,
sum.
sorry, okay, yeah, I probably should have, okay.
Yeah,
cool.
I said
I
that.
get what you're doing now. I'm sorry.
Okay, I probably should have, yeah.
Yeah, it's not a 1 over n. It's the average over, the treatment group is the average over how many people are treated. Right?
This one?
Yeah, it's a ratio estimator.
Okay.
No, just, you forget a pi. Let's say this was a randomized thing.
Right.
When it's estimating that treatment group, the average, you just average over all the people treated, their treatment. Right? So the n is not an n, it's the how many people treated.
Right, but that is, okay. I can, do I write it on the board or something?
You can write
it. Let me write it something like that. So basically, this was, so this was my arc, right?
Yeah.
I can write this as this. Right?
Yes, you can, yeah.
Right, and
yeah, so that's right, this one's right.
Okay.
I'm saying this one's right, but this, because the n is already, the pi is already 1 over.
Right.
Right, yeah, that's it.
Okay.
But but that's also said that if you have summing over these pi x themselves, right, it will be like the way you want to standardize, it will be still, these two estimate actions a little bit different.
Right, that is true.
They're two different, yeah. But I actually prefer the one he said.
Right.
Yeah.
So yeah,
it's a little less biased. Yeah.
Right. So yeah. So what you are saying, like, so that estimator, when you actually divide by 1 over pi xi, so some kind of a normalization of the weights.
Yeah.
That is more preferred due to like mathematical reasons, because I'll not go over this, but these estimators have very high bias. Sorry, very high variance if pi xi are very small.
Yeah.
That estimator has lower variance, but that is a little biased.
It's a little biased.
Right.
It's a bias for the trade-off.
Right. And sometimes people actually trade off the bias for the variance.
Yeah.
Bias.
Yeah. You're right. It's more stable.
But okay, but I'm going to, because that's a little complicated. So this is like the classical ITW estimator. So
but let me, I know you want to move on, but there's a really important thing. There's a really important thing for people to get it about this propensity score, okay? This is probably the statistician's the best thing that invention here. Because if you have these the fundamental problem of the two groups, when you say they're confounding factor, is because there's something different other than that treatment you assign to it, right? So it's a compare apples with oranges, right? Randomization allows you to say, statistically speaking, these two groups are the same apple, same orange, right? So when you want to create, when you have these confounding factors, you want to create, so people say, okay, how about I'm going to select people, I'm going to look at all the background. If I have all the X's, right, I can try to look at how many people have the same X for one group and how many for the other group. I can artificially try to match them. But here's the problem. When artificially trying to match them, particularly when X is large, you run out of sample size, right? You can't find the people is just exactly your age. You want to balance these two groups. The best part of the statistical argument is saying you don't need to match on so many different things. You only need to match on one score. If you can match on a score, is their probability be treated or not treated? If you match people on the same score, That's all you need. And that's the huge improvement, because, you know, matching on 10,000 things, you cannot do it. But this is just a match on one score. Now there's a magic here, right? The magic is I know what the score is.
Yeah, and it seems like you need as much data to actually determine the appropriate function. For that
Well,
score.
not necessarily. No.
Yeah,
Here's the fun part. It turned out that this is an empirical you can verify. People just run a logistic regression. Okay.
Yeah.
Okay, just run a logistic regression. Then you can check on that. You do the match. Then you check after matching them. You look at their backgrounds, like does their age, you know, same as they do very well. It turned out that it was actually interesting. This matching itself is pretty robust to what function you choose.
Okay.
All right, because it's just trying to empirical bet, especially when you have lots of data. The problem you run into sometimes, this is why you have the positivity assumptions. You don't have these two groups, like they don't have overlap. That's the whole problem. You have one group has a treatment this, the other treatment. You can't find they have much overlap. Then you have no common ground and these kind of assumptions is essentially saying, well, there will be some people they could have gone to either group. That's where the comparison is, right? If there's no people could ever, they can only go one group, the other treatment, you can never compare them. So the vulnerability of this thing is depending on how many people actually have the overlap. And your point is having many data helps of that, right? So there's no free lunch here, but the deep inside is you don't need to match on all these individual. It's all match on what is the probability they belong to each. Because randomization make that happen, right? Everybody has same probability to belong to one group or the other. This is artificial afterwards to say, can we engineer these two groups? So the people in this group, they roughly have the same probability have gone to either the treatment group or the other group. And that's where the magic happens.
Makes sense.
Yeah.
Jeff has a question. I think he has to leave, but Jeff, do you want to ask the question?
Oh, yes. I don't want to interrupt, but I have to leave fairly soon. I was just curious. A long time ago, I was a little familiar with some stuff that Clark Glimore, sorry, I misspelled his name, is Glimore. There was a program at CMU that I think is still in existence. Is that related at all to the concepts you're developing here?
I'm not very sure about. I'm not very sure about what you are talking about. Can you give me like more context for this?
I don't know.
There's an algorithm, the Peter Clark algorithm.
Oh, okay.
Which is like the two first names of people that.
Okay. So Clark Gilmore from Clark. Okay, yeah. No, no, I don't think so. So I think what I am actually trying to. Okay. So what I'm actually trying to present here is a way you can actually estimate the average potential, average treatment effect. I think that algorithm by Peter and Clark, what it actually tries to do is something different. It does something like if you have like a system of variables, it kind of tries to find like kind of a direction of causality between those systems. So for example, if you have like 4 variables, which is, we observed from an experiment, that algorithm actually tries to see whether we can tell like which variable caused an effect of which other variable. That's what that algorithm does. What I am actually trying to do is like, how do you even talk about this causality? Like, so what exactly do you even mean by causality? I'm trying to define that. So it's maybe like a, step 0 before we try to talk about like Peter and Clark algorithm, if that makes sense.
Yeah. Okay.
Sorry, go ahead, Jeff.
Yeah.
I'm trying to.
Sure.
Anyway, the Carnegie Mellon work I think was pretty interesting, but like I said on the note, I was never convinced. I think they were sort of using Bayes networks, probabilistic networks, and that kind of thing, and I was never convinced that it really avoided this fundamental issue that in astronomy and time series in particular, often you don't even know what the potential confounding things might be. But
that is true.
Anyway, and just quickly, if I understood something that you said, it suggests that maybe independence is a more important concept than a lack of correlation. And so does that suggest that using measures of independence would be useful in analyzing real data?
Uh,
Like using mutual information type quantities, and there's some literature on statistical methods for estimating independence, which of course is a much stronger
right. So,
thing. Yeah.
so the thing okay. So what we are presenting here is, let's say, a statistically asking the question, what does causality even mean? Like, what exactly would I say when I say like there is a causal effect? And that exactly is defined by a parameter tau. And then I'm basically talking about methods on how you can estimate tau under a variety of settings. I think what the questions that you are asking is more relevant in this setting, where you are not really interested in like defining what causality is. You want to establish like a set of relation between a set of different variables, which is called like structural causal modeling. And you're basically trying to see whether there is a causal association between two variables or not. Now, actually, if you actually have taken account of all possible confounders, in that particular case, correlation does imply causation. So in the case where your treatment is completely independent of your outcome, in that case, correlation does, if you still observe correlation, then that does actually imply causation. Now, that's what I guess is relevant in these kind of situation, where people actually try to do is basically they try to control for all possible confounders, and then they try to find a measure of association between two variables. In that, if you are only interested in that, yes, in that case, we can talk about various measures of conditional independence and those kind of things. Here, I'm talking about a completely different quantity. Like it is like, how do you statistically estimate causation? So for example, even if you establish like two things are conditionally independent, you still don't know like how much, what is that extent of causality? Like how can you assess that effect, which you can do using the thing tau that I suggested. So I want to really say that one is a subset of others. The programming, the paper of CMU that you're talking about, I think that basically talked about the second problem. This is like maybe a step 0, as I was saying, is like, how do we even start understanding causation? If that makes it clear. Not sure.
Okay.
So I just want to make one point here that it is now 1:10, so you have maybe 15 minutes to cover the rest of your, how many, 13 slides?
I won't, but what I will do is probably, there were various points that were raised throughout this talk. Let's basically look at those slides that kind of answers those particular problems. And I'm going to skip the rest.
We never finish here anyway.
Yeah.
This is some sort of a record.
So math, this is the only thing which I have math, but so what this math shows is that if you define your IPW estimators like that, then they're actually unbiased. So you can actually prove that IPW estimator is unbiased. And now I'm gonna, and this is exactly what you call an IPW estimator. So you have an IPW estimator for the treated, you have an IPW estimator for the control, you take the difference. This is a very common estimator that people use in partial inference.
Is that making some assumption on your ability to estimate pi?
This
functional form of pi if x is continuous?
Yes, so this thing actually assumes that you exactly know pi xi. Okay. The moment you basically put a hat on it, at least if you don't have a consistent estimate, this is not a good estimator at all, right? Okay, I'll just quickly go over and say what people do and skip how people do it, in the sense that, so this is a problem. We don't know what pi xi is. So in that case, it might be tempting to replace a pi by pi hat, but how this estimator now performs is completely dependent on like how well you have estimated it. And that might depend on many strong assumptions that you have like no way to verify from your data. So what people do here is they do a very clever thing. And this is precisely the matching argument that Shaoli was saying, which is that, these propensity scores have this amazing balancing property, which is that if you weight the treatment group by this propensity score, they exactly look like the overall population. This is written a little mathematically here, which is, I have said that for every bounded function f, this weighted expectation is equal to this unweighted expectation, right? So for example, if this fx was like xi, xi squared, xi, then this would be, let's say, a moment. So what this relation says that a weighted treatment moment looks like the unweighted overall moment. So this is what we call the balancing property of matching estimators. So what people say is this. They say that, well, I don't know how to, so I don't have any assumptions on pi hat xi. I don't know how good I'll be able to estimate pi xi. How about I directly attack this property? So what people do is they basically replace this 1 over pi xi by a weight, and they try to find weights such that the weighted moments of your treatment group match with the unweighted moment of the control group. And then what they do is instead of using a 1 by pi hat xi, in place of that, they use it of their weights. So these are called like weighing estimators. And again, I'm not really going into the details of how people do it, but that's like one thing that exists. And it actually exactly exploits the philosophy that Charlie suggested.
The very quick thing, the philosophy here is a very simple one. If you oversample the sample, you downweight it. If you have not sampled, you upweight it. So the inverse probability sample. That's it. They're used all over the place. And the game here is how they estimated these pies. Then you have, if you have some group, you can anchor them. You're not matching it. That give you some weight. So there's a lot of those plays you can do there.
Is the same technique that the polling people do with the
yes, exactly.
Yeah, exactly. Yeah.
Non-response bias, and then in computation called important sample. You sample from something else. It does not match magic here. Just balancing the probability.
This idea is have several manifestations.
Yeah. Okay. Many where you see that.
Okay. I'll skip everything now, and okay, I'll talk about this, which is that we were always concerned, like so whatever I did up till so far actually assumed that I know the entire set of confounders, but that never happens in reality, right? So the assumption of unconfoundedness is not wrong, but the fact that I'm assuming that I observe all the confounders, that is problematic. That can never happen. And especially I'm interested in scientific questions. I'm even interested in the scientific questions because I don't know things about it. Then how can I tell this is all possible set of confounders and there is nothing more than that can confound? So usually this is the case. You do have unconfoundedness, but out of these confounders, you only get to observe the xi's. You never observe the ui's. So the question is, what do we do in this situation? Honestly, to the best of my knowledge, there is not really much we can do. What we have not observed, I cannot tell what effect it has on my analysis, how that would change my analysis. But what people actually do is they try to assess what would be the effect of an unmeasured confounder on my analysis. Here's an example how this, there's a historical example of how this is done. So R.A. Fisher, who is also regarded as a father of modern statistics, he used to believe, so he came up with these vague ideas of causal inference, but this potential outcome framework, that was not there. So Fisher once argued that, so he was a strong believer of the fact that if you cannot do a randomized control trial, then you cannot establish causation. He said that, there is actually no causal relation between smoking and lung cancer. It's actually caused by a common gene. And there is only correlation you're observing, and there is no causation. So Cornfield, he came up with a very clever argument. So he did some experiments, and he showed that if Fisher actually was right, then that would imply that we actually have a gene which is highly related to your propensity to smoke. That means if, so the correlation that we're observing between lung cancer and smoking, if this was actually coming from that particular common gene, then that common gene, he showed it using some basic calculation, then that presence of that common gene makes you very, very likely of being a smoker. That does not happen. We know that that is not a medical thing. So that actually implies that maybe actually what we are observing is actually coming from a causal relation and not a mere correlation.
Well, how do we know that?
Yeah.
That's an entirely plausible hypothesis.
Well,
people get
we
a
know
lot
it
more from this and that drug. Maybe if you're nicotine receptors broken, you don't get.
So this comes from just say, so I'm giving you, let's say, a system of variables. So you have common gene, whether you're smoking and whether you have lung cancer or not. You have observed the probability of lung cancer given smoking. That's what you have estimated from your data, right? You can get, let's say, unconditional estimates of how many people have lung cancer, how many people have smoked. right? Thing is, you are just playing some probability games. You are using like very crude bounds, right? So, for example, I think he somewhere replaced some probability by that it is less than 1 or something. And it turned out that in that situation, he came up with this conclusion that probability of smoking, given that unconditional G, that has to be something, that probability has to be greater than 90%. It might happen that you will not be able to do it in a reality. It's not let's say, foolproof method. It's just that based on the data, he made this argument.
So I guess the key thing there is additional information, right? Because you look at the population, yes, by the subpopulation, people who have lung cancer, it's not enough. But you also have information like how many people are smoking in the population, how many people have lung cancer in the population, right? You basically the probability argument and say, well, yes, everything's possible, but they're so unlikely, right? It's just the way you do it. By the way, Fisher is a heavy smoker, so you can see about it.
Yeah, I imagine you are.
I don't know whether it's appropriate to mention it, but to make things worse, Fisher actually died of lung cancer.
Yeah, I mean, he did that. Well, actually, he died from a complication of surgery.
Oh,
yeah.
But
he died the year I was born, so I remember it. 1963.
Okay.
Yeah, I remember everything from 1971.
All right. So this is something we call sensitivity analysis, in which we cannot, let's say, modify our analysis for an unmeasured confounder, but we ask this question like, how likely is that whatever I'm observing is actually not coming from my observed confounders, but an unobserved confounders?
This actually, I don't know, we have a colleague at, where is he, the biostat or the epidemiology, Tyler Vandervee, right? He has developed a whole series called the E-value.
Yes.
Somewhere the E-value. E-value is basically, it's very clever. It's basically saying, okay, it's a kind of example kind of argument. Say if there's a confounding factor, I need to show like how strong that confounding factor has to be in order for this to happen. And then everybody argues, well, that's unlikely, and that's a one way to kind of put down.
No, it would have to be extremely strong.
Yeah, exactly.
Yeah.
So if it is, so if you observe like unlikely conclusions, then you conclude that, well, probably it's not coming from an unmeasured confounder. Yeah. But if you observe like likely conclusions, then you cannot say anything.
Yeah.
Okay. So, okay.
Another question?
Oh, sorry.
Yes, go ahead.
In your example of the confounders, the common shape, we need to like look over all confounders.
No. So that is true. I mean, so yeah, that is definitely true. But this guy was actually trying to prove Fisher wrong. Right. So he was saying that, so suppose if common gene is the only confounder, he actually tried to find the probabilities. Yeah, in general, you need to do that, right? And there are complicated methods people do it, but I don't know. How long can I speak?
10 more minutes.
Okay.
But,
this is math and I don't want to do this. So essentially what people do is something like this. So the way you do it is like this. So you have a method using which you have estimated your average treatment effect, right? And so you have to estimate like expectations, probabilities. These assume like you have made some model assumptions and those kind of things. So this is like one way of doing a sensitivity analysis, depending on what estimator you're using, So there is not, let's say, a black box way of doing sensitivity analysis that whatever method I have, I fit it in and I get a result. It's not like that. Depending on how your method is, you do a sensitivity analysis, but the principles are the same. So what people say that, okay, I have not observed an unmeasured confounder. I have not observed the unmeasured confounder, but suppose the unmeasured confounder is there. So what they do is like taking that unmeasured confounder into an account, they write down their entire statistical system. So that might mean, ignore everything what I'm writing here, but that might mean like, you have like additional parameters in your entire statistical model. For example, if you were, let's say, previously trying to model just the, probability of getting a treatment, you would have considered it, constant gamma. But now I'm assuming that I have an unmeasured confounder, so it actually depends on some parameters. The thing is that these parameters, you will never be able to observe them because you're not observing the confounder. Let's call them sensitivity parameters. One way of doing sensitivity analysis is that you first fix these parameters, like for any particular value, and then get your estimate of average treatment effect. Whatever you are doing, that would depend on whatever model you have assumed. And then what you do is you basically vary these parameters on a grid of values. And then you see how your average treatment effect is changing. the idea is that, if it is the case that you really need to take extreme values of these parameters for your conclusion to change, that actually kind of suggests that my analysis is, kind of resilient to the presence of unmeasured confounders. But if it is the case that, even a small change in this parameter drastically throws off your whatever conclusion you have drawn, that kind of implies that, well, I cannot reliably say that my estimate is, my analysis is like sound, because an unmeasured confounder can clearly throw that off. So this is not saying that my analysis, that there are no unmeasured confounders. What this is saying is that even if my unmeasured confounders are present, it is not going to affect whatever analysis I have currently produced. And this is like one way. And now you might be thinking like there are like plethora of ways I can actually do a sensitivity analysis. There could have been like 100 more parameters like that. People have actually tried to, for example, e-value is definitely one way in which, you have reduced everything to one single parameter. So people have done clever things here. So, but I'm not going into that. But the idea was that, I just want to talk about how people, how people really talk about, consider this case when they have not observed confounders. Okay. I will skip everything here and I'll conclude. Yeah. I think I have kind of, so I don't intend this thing to be, let's say, I don't expect that if you did not know causal inference, then after looking at this talk, you now know causal inference. But what I want this to be like a motivation of like, what is the basic challenge? Like, what is like the basic core idea on which people are trying to base their principles on? So you understand, like, in this entire thing that I have talked about, the basic initial problem was that I am not observing both the outcomes, and the outcome is somehow related to my treatment, and I don't know that relation, right? This is that one problem people try to get around in different settings, right? So I talked about potential outcomes. In many settings, this potential outcome framework does not hold. For example, what happens now if your treatment is, let's say, continuous outcome? So for example, now, instead of whether you're treating me or not treating me, you're interested in saying that if you give me like one particular dose of a drug, how much fluctuation will it bring about in my blood pressure? Now here, your potential outcomes are, let's say, it's on a continuous grid. Now, anything that we have talked about so far, there is no treatment group here because there is no treatment. Treatment are like any possible dose. But so definitely there, people completely change their analysis. But what I'm trying to say is that this basic idea is that, I have to in some way understand how my treatment, how my covariates are affecting my treatment allocation. These basic ideas always remain constant. And that's like, one way of, kind of summarizing what causal thinking is. There's that. And yes, and of course, these frameworks are like very flexible, and many scientific questions that we develop from different areas actually fall into this regime. A closely related idea of causal inference is missing data analysis, where you observe the data, but some of those rows are missing. And like, how do you do that? In that case, we basically kind of treat missingness and non-missingness as being treated and not treated. And then you exactly use the same framework. And you understand, like, this might be a real thing. For example, if you go on a survey and you ask people whether you have ever done a murder or not, most of the people will not answer questions, or will refuse to answer questions. So whatever data you observe, you will see that most of the people have said that, they have never committed a murder. But that's precisely because those who have committed a murder, they won't ever participate in this survey. So this kind of right, counterfactual problems.
It's an anonymous survey.
Okay. And I'll now talk about this. So this is really a new discovery, which is called conformal inference, which now lets you, which kind of have helped us to even talk about like confidence intervals on individual treatment effects. So for example, yeah, this is something I don't want to talk about much on. Initially, we were actually talking about like expectations. These kind of methods actually allow you to make inference on like my individual treatment effect and form a confidence interval. Let's not talk about that. And yeah, I feel like this is all I intended to. Yeah, thank you very much. All right.
Thank you. We meant to have lots of discussions, but I do have one more thing to add, which I think is very important, particularly for you guys to think about. There's another technique here, which is people use a lot, which is called trying to seek quasi experiment existing in the nature. You cannot do it, but there's some mechanism that happened. You can think that as like a randomized trial. So we'll give you a very specific example. I was editing the special issues on for Harvard Data Science Review. We talk about how do you estimate the value of a data set. Okay. Now there's no intrinsic value of a data set until somebody uses it. So now they're trying to do this particular example. There's a whole article you guys probably want to read. They try to estimate what is the value of the value of the Landsat data, right? The satellite data. What's the value of that for the industry, which they're trying to find where the gold mine is. Okay. So now, so what they did is Landsat was known to have some technical errors. There are years that some error happens that these Landsat images, like some areas, they were not available. And there are other times you have the clouds. So the data was not available. Now you argue that this kind of mechanism is unrelated to whether this place where they had a gold mine or not. While these errors are not invented to cover things. Now, cloud might be.
Uncover depends on latitude.
Yeah, right. Cloud could be, right? So this is a good argument, right? Cloud could be, but you can see where they're going, right? Yeah. The idea that if you can argue, now you have places where the treatment is they have the Landsat data, others you don't. If you can argue the selection mechanism is unrelated to the question I want to answer, you have a quasi experiment. And they, based on that, they estimate the value of Landsat data was about $7 billion. In fact, the private commercial companies are using Landsat data a lot to navigate where the gold mine is. So they made a comparison. But that made the study incredibly interesting, right? Because it takes a lot of thinking, your contextual thinking, to argue whether, but the thinking is exactly experiment design thinking. And the beauty of that is that you need the best part of randomized trial is saying, whatever the outcome you want to look at, it's all fine because it's randomized. In those studies, you only need to find a mechanism of selection that is uncorrelated with the question you want to answer. And that gives you at least a more valid argument than mindless to just say, well, here was available, here's not available, right? So maybe, you're right. Maybe we should not think about the cloud, because that could be related to the area, but we could think about the technical errors if that has happened by accident. Another thing people use in the legal study, right? There are lots of things to say, whether a judge is, biased or not. How do you establish those things? It happens some court, because there are too many cases. They randomly assign the cases to different judges. Not for statistical purpose, just for distribute the workload. Yeah. Retrospectively, that become actually was randomized. That you can see how because this thing was signed, right? So basically, there's a lot of clever thinking is thinking about what is the mechanism can make you claim that kind of quasi-randomized experiment. And I think that might relate to what you're saying. When you have lots of data, you can think about a mechanism for which is, well, you can argue, and that will give you a causal framework to think about.
Yeah, and you're still kind of stuck trying to claim that you thought of all the compounding factors.
Sure.
But if you
but it's better.
Can think of all the compounding factors and you have infinite data, then you're kind of
There's no guarantee, but it's better, right? Like most people probably think about the satellite image errors not related to where the gold was. Yeah, pretty solid argument. But you never know, right? Who knows?
Yeah, any conclusions are only provisional.
Yeah.
Go ahead.
But that's why we always have jobs.
Yeah.
So this quality experiment thing has been in social science a lot. You cannot do, like the pandemic itself creates a lot of quality experiment. We force everybody to stay home, So yeah, a lot of things to say. But that makes them more interesting, like the framework. Truly do randomized experiment is just the ideal situation.
So now I really want to know what conformal inference is. The third half of the talk is usually the most interesting.
I can talk about that. So it's a completely different thing. So you have a machine learning algorithm. It's a black box machine learning algorithm that you have gotten. What does it do? It takes an xi and it gives you a prediction, right? So for example, suppose I'm trying to predict my blood pressure depending on some other biomarker, right? Now the thing is that there is randomness, right? So suppose I tell you that my blood pressure is like 138, my systolic blood pressure. Now, if my blood pressure is above 140, then you diagnose me with hypertension. The question is, if my machine learning algorithm predicts that my systolic blood pressure is 138, do I have hypertension? The problem on this thing is that, there is randomness. What I know for sure that whatever my algorithm has predicted is a wrong blood pressure. My blood pressure is not 138, right? So how do I know whether it is above 141? So what conformal inference does is that, it makes absolutely minimal assumptions on your data. And then basically it takes any black box algorithm and instead of predicting a number, it now predicts a confidence set. So now you will not get 138. You will get something maybe like 120 and 139.
You get a distribution.
No, you will get a confidence interval now. So, but the algorithm will say that, my blood pressure is between 120 and 139 with 90% or 99% probability. Now I'm like 99% sure that I do not have hypertension. So people have actually used this framework to get actually estimates of these things, individual treatment effects. So you don't really get an individual estimate, but you get a confidence. And then you can see whether 0 is in this confidence interval or not. If it's 0 is there, then it tells there is no average treatment, there is no treatment effect.
I have to say that the people who work on this, I work on this too, is a bit hype about this methodology. Okay, I tell you what it is. It's actually incredibly simple, right? The fundamental assumption is like individuals are not learnable unless I assume that other individuals looks like me. Yeah. So if you assume there are a group of people is like ID, right? All I have to do is very simple. If I have 100 people and I'm the other person, I can look at a histogram of 100 people, give me a histogram, I can place where I am. I can get a confidence interval just from the histogram, right? Yeah. Right there, I can do. That's pretty much what's conformal to. That's slightly more complicated. Basically, so that's what they call the minimal assumption because there's no model assumptions. But the fundamental assumptions, I have people exchangeable with me. Now they don't have to be ID, they just need to be exchangeable. So they come up with this so-called non-parametric that kind of interval with the correct coverage, because if you have this like if I'm exchangeable with others, you can see the permutation argument to get this interval. That's what it does. Now the beauty of that, given the beauty of that is we really have that, it doesn't care what the methodology you're using. Right? That's why it become a black box. People get very excited. But all it does is rely on this. It doesn't give you kind of individual score for you, but it's individual because you have a population too. The really hard problem is what you talk about is the infinite kind of a treatment things. Then, if I'm unique, then the idea is I have to find people approximately like me, and that gets a lot more complicated. Right? But all stars look the same, right? You guys don't have this problem.
No, actually, there was a talk at this workshop relative to there was a talk about some similar idea for photometric redshift. Oh, yeah. Like what you want is a confidence interval in your photometric redshift for galaxies that have exactly the same photometry. So
okay,
that's the same thing.
Yeah.
I think that was what the guy was talking about.
Yeah. Okay. Yeah, that seems plausible. Right? Yeah. That seems plausible. There's no free lunch here, other than you come to this class.
Yes.
Yeah.
All right. So
this is great. This is a good discussion.
Thank you.
Souhardya. Thank you.
So it's past 1:30, and we should probably let everyone go unless they have any last minute questions from the peanut gallery. If not, I guess let's sign off. Unless you want to talk, CHASC is still here. If you want to talk about the maxims. He can see you.
I just came. Hello everyone. Sorry, I had a class, so I couldn't join. And I'm wondering.
So next week, you're talking, right? Okay. Do we have an abstract entitled yet? Yes.